In this video, we will introduce the concept of complex numbers and the basic mathematical operations that can be performed on complex numbers. Let's take a look at these three quadratic equations. One similar point between the three of them is that their discriminants, or b squared minus 4ac, are negative. From O-level math, we have learned that when the discriminant of a quadratic equation is negative, it means that there are no real roots, since we will not be able to solve for the solutions with just real numbers. However, this does not mean that the equation has no roots. It just means that the quadratic equation has roots that cannot be simply represented using real numbers, and for this type of roots, we call them complex roots. Let's try to solve the first two equations. For the equation z squared plus 1 equals to 0, we can move the 1 over to the right hand side to get z squared equals to minus 1. And thereafter, we can solve for z by taking the square roots on both sides to yield z equals to plus minus of square root of minus 1, which does not make sense as of now, since we have been taught that we cannot square root any negative numbers. Let's leave it as it is for now and move on to solve the second equation. We can apply the quadratic formula to solve for w, and after simplification, we will end up with w equals to minus 1 plus minus square root of negative 1, which again does not make much sense due to the square root. Now, what I will do is, since square root minus 1 is not real, I shall call it the imaginary number and let the symbol I represent it. So the solutions above can be expressed in terms of a combination of a real number and I, the imaginary number. This combination of real and imaginary numbers is called a complex number. A complex number can be expressed in three forms, and we will only be covering the basic form in this video. The basic form, or Cartesian form, of a complex number is in the form x plus iy, where x is the real part of the complex number and y is the imaginary part of the complex number. One way to represent the real and imaginary components of a complex number is Re bracket z, which means the real part of z, and Im bracket z, which means the imaginary part of z. Note that we do not need to write the I down when writing the imaginary part of complex number z. So we do not say that Im of z equals to yi, okay? Since y alone is going to be the imaginary component of the complex number. In example 1, we need to solve this quadratic equation for the roots. So we can simply apply the quadratic formula. X will be equals to minus 5 plus minus square root of 5 square minus 4 times 2 times 8 over 2 times 2. So we can simplify the term within the square root first to get minus 5 plus minus square root of negative 39 divided by 4. And we can break it up into minus 5 over 4 plus minus square root of negative 39. I'm going to write it as square root 39 square root minus 1 divided by 4. And this square root of minus 1 can be represented using I, and therefore this term becomes minus 5 over 4 plus minus square root of 39 over 4i. And these are the two roots of the quadratic equation. We can treat the imaginary number I as a constant and perform operations on it like how we do so in algebra. For addition, we can simply add up the real component and the imaginary component separately. So for the addition of 1 plus 2i and 3 plus 4i, it is the same as us calculating 1 plus 3 for the real components 1 and 3 plus 2 plus 4 multiplied by I on the outside for the two imaginary components. And this gives us 4 plus 6i. Likewise, for subtraction, we can simply take the difference between the real and imaginary components separately. And thus, for the subtraction of 5 plus 2i and 3 plus 4i, it is the same as calculating 5 minus 3 plus 2 minus 4 times I, which gives us 2 minus 2i. For multiplication, we first consider I square. We know that since I is equals to square root of minus 1, I square must therefore give us minus 1. Also, I cube is the same as I square times I, which is therefore the same as minus I, and I power 4 will be the same as I square times I square, which gives us a 1. So these are some useful identities that we can remember. And with this, we can now perform multiplication of complex numbers by expanding the terms in each complex number, like using algebraic multiplication. So for 1 plus 2i times 3 minus 4i, we can expand it into 1 times 3 plus 1 times negative 4i for this second term, plus 2i times 3 for this, and 2i times negative 4i for the last one. And we can try to simplify them. First, we get a 3 from 1 times 3 minus 4i plus 6i, and the last term is minus 8i square. And we know that I square is minus 1, therefore this term is the same as plus 8. And finally, if we simplify everything, it will become 11 plus 2i. The next operation is something that is unique to complex numbers, and it is called the conjugate operation. And it is represented by the asterisk behind the complex number. What the conjugate does is to change the sign of the imaginary component. So for 1 plus 2i, its conjugate becomes 1 minus 2i. And likewise, for the complex number 1 minus 2i, its conjugate will become 1 plus 2i. So we say that 1 plus 2i and 1 minus 2i form a conjugate pair. The product of a conjugate pair always gives us a real number. For example, if I have x plus iy multiplied by x plus iy star, which means x minus iy, I will get x plus yi multiplied by x minus yi. This is the form of a plus b, a minus b, and therefore it can be simplified into x square minus yi square. And this becomes x square plus y square, since we have a minus here and another minus from I square. For division, the approach is very similar to rationalizing surds. If we have 1 plus 2i over 3 plus 4i, what we have to do is to multiply this fraction by the conjugate of the denominator over the conjugate of the denominator, which means we can multiply it by 3 minus 4i over 3 minus 4i. You get 1 plus 2i over 3 minus 4i, sorry, 3 plus 4i here, multiplied by 3 minus 4i over 3 minus 4i. The reason for doing so is so that the denominator will become a real number if we multiply it by its conjugate. As shown over here, it will just become a real number. And we have to simplify the entire term by expanding it. So we get 11 plus 2i in the numerator, and in the denominator it will be 3 square plus 4 square, which is 25, and therefore this complex number becomes 11 over 25 plus 2 over 25i. We can also derive a simple expression for 1 over I using the same method. So we have 1 over I, which becomes 1 over I multiplied by negative I over negative I. In the denominator, we have negative I square, and in the numerator, we have negative I. So we can't do anything about the numerator, but the denominator just becomes a 1, and therefore 1 over I becomes negative I. And this is a common identity that we should be familiar with. In example 2, we are given the complex numbers z and w, and we are asked to simplify this complex number into the basic x plus iy form. So we start by doing a substitution of z and w. W minus 2z star divided by z plus w is the same as 1 plus 2i minus 2 times of 3 minus 5i star divided by 3 minus 5i plus 1 plus 2i. So we try to simplify slightly first. In the numerator, we can simplify by removing the conjugate to get 1 plus 2i minus 2 times of 3 plus 5i divided by the denominator, which becomes 4 minus 3i. So we can further simplify the numerator into minus 5 minus 8i divided by 4 minus 3i. So now it is a division and we will need to rationalize it so that it can be changed into the x plus iy form. And we do so by multiplying by the conjugate of the denominator, 4 plus 3i over 4 plus 3i. So we now have to simplify the numerator and denominator separately. In the numerator, we get negative 20 minus 15i minus 32i and plus 24 divided by 4 square plus 3 square, which can be simplified into 4 over 25 minus 47 over 25i. In example 3, I need to find out what is the square root of the complex number negative 21 plus 20i, which should give me another complex number. So I can say that the complex number a plus bi represents the square root of negative 21 plus 20i. And I want to solve for the values of a and b, which will thus give me the resulting complex number for the square root. So first, I'm going to square both sides to get a plus bi squared equals to negative 21 plus 20i. Now I can simplify the left hand side to give me a squared plus 2abi minus b squared equals to negative 21 plus 20i. So now what I can do is to compare the real terms versus the imaginary terms. And I can say that a squared minus b squared equals to negative 21, and I'll call this equation 1. And I can also say that 2ab must be equals to 20, which means that I can rewrite b as 10 over a, and I'll call this equation 2. So now I have two equations with two unknowns a and b. I just have to solve simultaneous equations over here, and I'm going to substitute equation 2 into equation 1, which gives me a squared minus 100 over a squared equals to minus 21. And if I cross multiply everything by a squared, this gives me a power 4 or a squared squared plus 21a squared minus 100 equals to 0. So essentially, although this is a power 4 equation, we can solve it like a quadratic equation. And we can factorize it to give us a squared minus 4 times a squared plus 25 equals to 0. And therefore, we get a squared equals to 4 or negative 25. And of course, we have to reject a squared equals to minus 25 because we will not get a real value for a. And we note that in the form of a plus bi, both a and b should be real numbers. And therefore, from here, we know that a can either be minus 2 or positive 2, and correspondingly, b, which is 10 over a, will become minus 5 or positive 5. And therefore, we know that the square root of negative 21 plus 20i can either be minus 2 minus 5i, or it can be 2 plus 5i. And that's it. In example 4, we have to solve this equation for z, but we cannot do so directly because there is the conjugate term over here, which makes it more complicated. So what we have to do for this kind of question is to let the complex number we want to solve be a plus bi and do a substitution. So therefore, we will have a plus bi plus I minus 2 whole thing star equals to 2 times a plus bi minus 4. And we try to simplify everything first and see what happens. So on the left hand side, within the square bracket, we will have a minus 2 plus b plus 1 I star equals to, on the right hand side, 2a minus 4 plus 2b times I. So on the left hand side, we can simplify further by removing the conjugate to get a minus 2 minus b plus 1 times I equals to 2a minus 4 plus 2b times I. And now we can compare the real components versus the imaginary components. And therefore, we have a minus 2 equals to 2a minus 4, which gives us a equals to 2. Also, we have minus b minus 1 equals to 2b, which tells us that b is equal to negative 1/3. And therefore, we can conclude that the complex number z, after we solve this equation, should be 2 minus 1/3 I. We can also solve simultaneous equations involving two complex numbers. So if we have this set of simultaneous equations, I'm going to name the first one as equation 1, the second as equation 2, and solve them the usual way, like how we solve simultaneous equations in algebraic equations. So I'm going to make use of the elimination method. Equation 1 plus 2 times of equation 2, it will give me z minus 2w plus 6iz plus 2w equals to minus 9 plus 4i plus 22. And the reason for me doing so is because I can see that there is a minus 2w and a plus w, and they will be able to cancel each other out if I multiply 2 to the second equation, like this. And therefore, I have eliminated all the w's in my equation, and I'm left with z 1 plus 6i equals to 13 plus 4i. And I can now manipulate this equation to get z, which is 13 plus 4i over 1 plus 6i. But of course, I cannot stop over here because this is not of the z equals to x plus iy form, and I have to always express my complex numbers in the standard kind of forms. So I'm going to rationalize it now, multiply it by 1 minus 6i over 1 minus 6i. In the numerator, I will get 13 minus 78i plus 4i plus 24. And in the denominator, it will be 1 square plus 6 square. So if we simplify, I will get 37 minus 74i divided by 37, which becomes 1 minus 2i. And once we have found z, we can find out w pretty easily by using equation 2. Since from equation 2, I know that w can be written as 11 minus 3iz, which is 11 minus 3i times 1 minus 2i. So 11 minus 3i minus 6, which gives me 5 minus 3i.